this is the second part. Let's continue with the next example. So the second part will be totally different topics. We will be talking about logarithm defined as an integral. And in the last part, I will talk about integration by parts. Okay, so in fact, we will be computing integrals of 1 over x dx form. So we will be using the integration rule of 1 over x dx. So look at the first example. Here, we can rewrite this integral in a better looking form like this one. For example, you can take this common multiple out from the expression so that you have this, and then how to take this integral. So for such integrals, so far we only covered which rule? Substitution rule. So we only know substitution rule by now. So we will be applying some substitution here. Either you will choose this part as your substitution or this part. So let's start trying with that part. If this is u, then du is dx, or let me write this down like 1 over 2 square root of x dx. Okay. So we need to express this part, this part in terms of u. In terms of du. We choose this part as u, and dx over square root of x can be written as 2 du. So the integral is, in fact, 2 comes out, 20. You can take also 20 out from the integration, 2 over 20. And then what we have inside the integral is du over u. So there is a rule for that. There is a rule for this integration. Recall. Let me put a very quick recall here. It is this rule. So this integral is evaluated as ln x. I need to put this arbitrary constant c because it is an indefinite integral. So be careful about this absolute value here, okay? This integral is evaluated as ln with this absolute sign. Okay, so the result here is 1 over 10 ln absolute sign of u plus c. Now let's also turn back to original variable. This is now back substitution. It is 1 over 10 ln u was 1 plus square root of x plus c. This plus c should be there because this is an indefinite integral, okay? So this exercise reminds us this integration rule. Okay, let's look at the next one. By the way, any question about this solution? Okay, let's do this one. Let's recall something. How do you take the integral of such forms? Integral of 2 to the power x dx. What is it? So to understand the result here, we can get help from this derivation rule because we need to find out some function whose derivative is 2 to the power x, right? So let's remember also this rule. Remember that 2 to the power x is derivated like that. So now I want to write here some function whose derivative is just 2 to the power x. So we need to get rid of this extra coefficient here. To get rid of it, of course, you need to write it inside parentheses as a denominator, right? Just to simplify it on the right-hand side. So the integration rule for 2 to the power x is 2 to the power x itself divided by ln 2 plus c, of course. Okay, so first of all, it is obvious that we need to apply this substitution first. Cosine 3t, then du is minus sine 3t dt. Okay, you see, if we choose this part as u, this turns out to be minus du, right? So here, what kind of integral we have? It is 5 to the power u minus du. You can easily evaluate it, right? But before evaluating, we need to understand the boundaries of u because this is a definite integral. So we need to transform the boundaries given for t here to the boundaries of u. So if t is 0, cosine 0 is 1. If t is 30 degrees, which is pi over 6, then what is u? Then cosine 3 pi over 6, which is pi over 2, cosine pi over 2 is 0. So the new boundaries should be written as from 1 to 0, okay? By the way, I think I forgot to put something here because, you know, by derivating cosine 3t, it is, of course, minus sine 3t, but you shouldn't forget to multiply with the derivative of the insider part, which is 3, okay? Like that. Then, this part should correspond to not just du, but there is also this extra coefficient here. It is minus du over 3. Okay, it is like that. Minus du over 3. So the result is minus 1 over 3. 5 to the power u du. How do you evaluate this integral? By using this rule, of course. It is itself divided by ln 5. And then you need to insert your upper lower boundaries for u. Lower boundary is 1, upper boundary is 0. So if you insert this upper lower boundaries, you will obtain the result as 1 over 3. 5 to the power 0 is 1 minus 5 to the power 1 is 5. So the result of this definite integral is this real number. Okay, any question about this solution? If not, I want to deal with the next example. Okay, so this is our next example, another definite integral question. And we need to start by applying some substitution. Either you will take this part as u or this part as u. We need to do this choice first. I want to make my choice with this part, right? I want to try this u. I don't know whether it will work or not. I just need to try. Without trying, without writing it, I cannot know whether it is working or not, right? So what is du? This is some function which is not a power function. Be careful. You cannot take the integral here like the power rule. No, this is completely wrong. Instead, you need to apply logarithmic differentiation here. How do you apply that? To apply logarithmic differentiation, okay. To find out what is du, we will apply logarithmic differentiation. So we will take ln of both sides. This is how you apply it. Ln u, ln x to the power x. So ln u is x times ln x. Take the derivative of both sides with respect to x. U prime of u prime divided by u is the derivative of the left-hand side. So here I am applying product rule, derivative of the first function times the second first times the derivative of the second function, like that. Okay, simplify. Then what is u prime? U prime is calculated like this. Ln x plus 1 times u, right? Where u is x to the power x. So this part comes from u. This is what u is. So let's change the notation from u prime to du over dx. You know, prime means x derivative of the given function ln x plus 1 x to the power x. Then what is du? Remember, we were searching for du. So du is ln x plus 1 times x to the power x. Then remember the original exercise, original example. This is exactly what we have found here for, of course, this dx also comes to the right-hand side as a product. So this is exactly what is written here inside the integral. So if you use this substitution, what you obtain for du is this expression, which is written inside the integral. So the integral is, in fact, is integral of just du, okay, with this substitution. And then what are the boundaries? You need to transform the boundaries to the boundaries of u now. These are the boundaries of x. So if x is 1, u is 1. X 1 to the power 1, right? If x is 3, what is u? U is 3 to the power 3, 27. So the new boundaries for u is 1 to 27. These are the new boundaries for you. And now I am ready to integrate, right? Integral of 1 is just u, and then you will insert upper lower boundaries for that from 1 to 27. So the result is 27 minus 1, which is 26, okay? So this is a very interesting question. Okay, any questions about this solution? If not, I want to move on with the next exercise. Okay, in this next example, we will apply integration by parts, okay? Let me make some recalls before we start solving it. Recall, integration by parts. Okay, so for integration by parts, we will apply it when substitution doesn't work. Okay, we choose u as some part of the function inside the integral, right, while applying substitution. But in this case, applying just this one variable substitution won't be enough. You will also need some new variable v, okay? So that's why we need to invent this new technique after covering substitution. Sometimes it is not enough to handle the integrals. We will need this new variable v. It works like this. So for some part of the question will be serving as u, the remaining part will be serving as dv, and the formula for integration by parts goes like that. uv minus integral v times du. Okay, so this is the integration by parts formula. How does it work? I will explain in the example, but before moving to the example, I want to make a very informal recall here. If you have two different types of functions inside your integral, like x cubed e to the power x or x squared cosine x, or I don't know, you see I am choosing different types of functions, or exponential function times trigonometric, or polynomial x to the power 0 is still a polynomial times logarithmic, or x to the power 0, which is 1 times inverse trigonometric function arctangent x. If you have such things inside your integral, which consist of products of two different type of functions, these types are written like that in this shortcut, where L stands for the logarithm function, A stands for arc tangent x, arc sine x, such inverse trigonometric functions, and so on. P stands for polynomials, T stands for trigonometric functions like sine x, cosine x, and all the other trigonometric functions, and E stands for the exponential functions like this. So these are different types of functions in calculus 1, and if you have product of any two types from this list, and if the integral is not evaluated by using substitution, then the best way to use is to apply integration by parts, okay? Let me write this down. If substitution doesn't work here, you need to apply integration by parts. Okay, so here I mean, if you have two different types of functions as a product, you can try to apply integration by parts. And here, if substitution doesn't work, what do I mean is this one. Let's look at this example, 2x dx. Here, this is still a product of two different types of functions, where one of them is a polynomial, the other one is exponential. But here, if you choose this part as u, the whole remaining part is du, right? And substitution perfectly works here. The result is e to the power u, where u is x squared. So I need to add this arbitrary constancy. You see, even if it is a product of polynomial and an exponential function, substitution works. Then you don't need to apply integration by parts. But sometimes, as it is here, substitution doesn't work, and you need some new variable v. Then integration by parts will save you. Okay, let's see how to apply it in this example. Look at this one. By the way, wait, I think I skipped this example. Let's start with it. Okay. Here we have x squared cosine 1 over 2x dx. Okay, let's see what happens here. Two types of two different types of functions where this is a polynomial and the second one is a trigonometric function. And there is no way that single substitution is working here. No, it's not working. Then you write our famous shortcut. This will help us, okay? In this list, which function comes first? You will be careful about which function comes first in this list. Then you will choose it as your u. Polynomial and trigonometric we have. Since polynomial comes first in our shortcut, I will choose the polynomial part as u, and the whole remaining part will serve as dv. That's how you need to choose u's and dv's from your expression, okay? By using this shortcut. Then we choose u, right? U is chosen correctly as x squared and dv is chosen correctly as cosine 1 over 2x dx. And then from u to du, you will pass by taking derivative. And from dv to v, you will pass by taking integral. Okay, this is our diagram. We will complete this diagram first. This is how you apply integration by parts. 2x dx, from dv to v, how do you integrate such things? Let me write a very quick rule here. This is integrated as sine kx over k plus arbitrary constant c. Okay, this is it, sine 1 over 2x over 1 over 2. We are not putting arbitrary constant c here. We will put it at the end, okay? So, and you will be following the direction of these arrows. These arrows, these directions shows you the formula of the integration by parts. If you forgot this formula, you will just follow these arrows. But as they tell you, u times v, as it is here, and v times du, as it is here, okay? Let's apply it. This is how you apply integration by parts. U times v minus integral v times du, okay? So 1 over 2 is 2 as a coefficient here, so 2 times 2 is 4, x sine 1 over 2x dx. Okay, that's what we obtain after applying integration by parts once. But look at here now. Again, if you choose this part as you cannot obtain x dx in du. So substitution is not working. We will apply one more integration by parts. We are writing Lapte again, polynomial trigonometric. P comes first, so polynomial part will be q, and the whole remaining part will serve as dv. Let's take 4 out from the integration, okay? 4 is here. So again, do the diagram. U du, dv to v. What is u? U is x, then du is just dx. dv is sine 1 over 2x dx, so integral of sine is minus cosine, and then you need to divide by 1 over 2, meaning that you have to multiply by 2. So it is like that. Now follow the directions of arrows, which means you are applying integration by parts. I will write the whole thing from the beginning on. X squared sine 1 over 2, I am writing here, 1 over 2 minus 4 times u times v is minus 2x cosine 1 over 2x minus integral this times this, okay? Another minus is here, so it is plus now, 2 times cosine 1 over 2x dx, okay? And you see, we have finally a simple integration that we can solve by just evaluating the integral. So the integral here is what? Integral of cosine is sine 1 over 2x multiplied by 2, okay? So the result is, let me write the whole result starting from the beginning on. Sine 1 over 2x minus plus, okay, plus 4 times 2 is 8. Cosine 1 over 2x minus 4 times 2 times 2 is 4, right? Another 4 minus 16 sine 1 over 2x plus a big arbitrary constant c. Don't forget to put this one here because you are evaluating an indefinite integral, okay? This was the example. Okay, so we applied 2 times integration by parts here, okay? You can apply it as many as you wish till you got the final result. Okay, any question about this solution where we applied integration by parts twice? First one is applied here by using this diagram. Second one is applied here by using the new diagram. Okay, let's move on. Next example is this one. Again, you see that we have 2 different types of function. One of them is polynomial, second one is logarithmic, and the substitution is not working. And then what we do, we start by writing labte to use while applying integration by parts. Polynomial and logarithmic, and L is the first letter. That's why we choose this logarithmic part as U, and the whole remaining part will serve as dv, okay? So start constructing your diagram then. dv to v, we need to pass. dv to v, okay. So what is u? U is chosen as ln x, then du is 1 over x dx. What is dv? It is x squared dx. Then v is the integral of it, x cubed over 3, right? And then you need to follow the directions of arrows, meaning that you're applying integration by parts. It goes like ln x, x cubed over 3, minus integral. This times this is x squared over 3 dx. And be careful, in this case, we have a definite integral. For definite integrals, you are applying those boundaries to here for x, and to here for the second integral coming from the formula of integration by parts. Let me write this down separately. If you have an integration by parts structure with boundaries like that, formula is the same, minus integral v times du, and you apply boundaries here and here, okay? Integration by parts, formula with the boundaries. Definite integral. Okay, that's what we have here. And this integral is just a simple integral. It is 1 over 3 x cubed over 3, right? You add 1 to the power, divide by the same power. Okay, then the final line, last line, will come from evaluating the boundaries. You will insert e to the power 4 for x and then 1, then you will subtract ln e to the power 4 times e to the power 4 cube divided by 3 minus ln. Now I am inserting 1 over 3. This part is the result of this expression minus now the second part. We have 1 over 9 x cubed, right? For x, I will first insert e to the power 4. And then for x, I will insert 1, take the difference like this. And this corresponds to the second part from 1 to e to the power 4, okay? So your result looks like that. And I think there is another cubed power here, which is here. Okay, so like this. By the way, this is, for example, 0. What is this? You can take 4 down and ln e is 1. So this first term is just 4, for example, and then you can write the overall result. Okay, any questions about this, about this solution where we applied integration by part once? Here is the diagram. Okay, if no questions, I want to move on with the next example. Okay, again, another integration by parts question, but you see we have lots of 5 coefficients everywhere. We can just get rid of it if we use the substitution. Let's choose this part as t. I am moving the variable from theta to t. Okay, I choose this substitution. Just to rewrite this integral in a simpler form, okay? Then dt is 5d theta. You see, this part already appears as dt, and I already named this part as t. So in the new variable, the integration is e to the power t sine t dt. This is better looking, right? Okay, let's deal with that one. This integral contains a function which consists of products of two different types of functions, and we cannot handle it by just a single substitution. This part is an exponential function and this part is trigonometric. So we understand that we need to apply integration by parts. And you see, one of them is trigonometric, the other one is exponential. T comes first in our shortcut. That's why trigonometric part should be chosen as U, and the whole remaining part will serve as dV. Let's construct the diagram now. U du from dV to V. Okay, U is chosen as sine t, then du is cosine t dt. dV is e to the power t dt. Integral of e to the power t is e to the power t again. And then apply integration by parts by following the directions of arrows. So it goes like e to the power t sine t minus integral this times this. So e to the power t cosine t dt. Okay. And then what happens? You see, for this integral, we need to apply integration by parts again, because products of two different functions. Again, trigonometric part will be chosen as du, and the full remaining part will serve as dv. Construct your diagram again. U du, dv to v. U is cosine t minus sine t dt is du. E to the power t dt is dv. Integral of it is e to the power t. Follow the directions of arrows. Then what happens? I will be writing the result from the beginning on e to the power t sine t here. Minus this times this, right? Cosine t e to the power t minus integral this times this. Be careful, there's another minus here, so I will put here plus e to the power t sine t dt. Then what is happening here? We notice something. Okay, we start with e to the power t sine t. We applied integration by parts once. By applying this diagram, we pass to this part. Then one more integration by parts. E to the power t cosine t. We turn back to sine t again. This seems like a cycle, right? This seems like an infinite cycle. If you apply one more integration by parts here, you will obtain cosine, then again sine, cosine. So this is in fact an infinite cycle. How to escape from this infinite cycle? There is a way, because look at the original question, e to the power t sine t. And it appears in the solution again. So this part is in fact the original question that we want to solve for. So if you treat it as an unknown, we were trying to solve this integral, right? And then it appears here inside your solution. So name it as I, for example, and treat it as an unknown. So we can solve this equation in terms of I easily, right? So to escape from that infinite cycle coming from applying integration by parts every step, you can just stop here because you notice that the original question is appearing in the solution. So you can do this like that. Minus I we have on the right. So take this I to the left as a plus I. So 2I is what? Is what we have on the right side. And then just solve for I. Okay, I is then e to the power t parenthesis sine t minus cosine t divided by 2 plus an big arbitrary constant c, because we are evaluating an indefinite integral here. You see, sometimes while applying integration by parts with exponential and trigonometric function, this happens. This may happen while applying integration by parts with exponential and sine cosine function, and then you know what to do. If your original question appears in your solution, you just stop there, name it as a very unknown, and then you will solve that equation in terms of that unknown. Okay, this is how to escape that infinite cycle. And then we also need to turn back to original variable. Remember, we applied one substitution at the beginning. So we need to insert 5 theta for t to give the final result. So t was 5 theta. We need to do back substitution here. So the result is e to the power 5 theta sine 5 theta cosine 5 theta divided by 2 plus t. Okay, that's your final result. Any question? T, instead of t's, we inserted 5 theta to turn back the original variable. Okay, if no question, I want to move on with the last example for today. It is this question. So whenever you have some function inside another like that, it is too obvious that you should start your solution by applying this substitution. Just to rewrite this integral in terms of the new variable u and just to have a better looking simple expression. So u is ln 9x. Then what is du? It is 1 over 9x times derivative of the insider part, which is 9 dx. Okay, so I start rewriting my integral in terms of the new variable u. Sine u, right? And what about this part? I need to find a way to express dx in terms of du's and u's. Is that possible? So look at this line. You simplify. So you see, I have x here. I should find a way to express x in terms of u. And from this line here, it is possible. Okay. If you take the exponential of both sides of this line, what you have is this one. So e to the power ln of something. You know, e and ln are inverse functions so that they will neutralize each other. Then what we have here is e to the power u. On the right side, we just have 9x. You see, this is the way how you can obtain an expression for x depending on u. X is e to the power u divided by 9. So this is solved as e to the power u divided by 9. That's why from here, then I understand I can write dx as, what is dx? In terms of u's and du's, it is e to the power u times du over 9. I mean, this expression times du, right? Okay, after having this, then I can insert it to here. So my aim was to express dx in terms of u's and du's, and I did it. So just insert it to here. E to the power u du over 9. Then what we have? 7 over 9 sine u e to the power u du. That's what we have. You see, instead of struggling with this integration, now I have a simpler form, in fact, which is solved exactly in the previous example. You see, we solved here e to the power t sine t dt, which is the same question that we have here, okay? Okay, so I won't be solving it again. It is the very same solution where we obtain the original question in the solution so that we name it as an unknown and solve for it. So I will just write, this is solved in the previous example. So just look above solution. And then, okay, it is in fact, let me take this solution from here, like copy paste, because it is the same question. So we will find e to the power u, parentheses, I am just looking here and writing the result, sine u minus cosine u divided by 2 plus an arbitrary constant c. And finally, as the last line, we need to turn back the original variable, back substitution. So for u, I need to insert, instead of u, I need to insert ln 9x. Okay. ln 9x, ln 9x, ln 9x. So sine of this minus cosine of this divided by 2 plus c. Okay, after inserting ln 9x, which is the substitution at the beginning, I am done. This is the final result of this exam. Okay. So in this question, there is something that I want to emphasize. If there is some function inside another one, obviously, for sure, you need to start by applying a substitution so that you can rewrite your integral in a simple looking form, and then you can just evaluate the integral and do some back substitutions to give the final result like that. Okay? Any question? If not,